In this problem, we have a book that starts at rest, has a mass of 3 kilograms, and it's pushed up a 30-degree ramp by a horizontal applied force of 20 newtons. It travels a distance of 0.5 meters, and we want to know if it starts at rest, what is the final velocity? Okay, so because we have the forces and because we know the distance, we should use the work kinetic energy theorem here because we don't know the time, so we don't want to use kinematics. So the first thing we should do is define our axes. So because the book moves in the direction parallel to the ramp, I'll call that the x direction, and perpendicular to the ramp will be the y direction. We can draw the free body diagram. And so we'll have the normal force, which is perpendicular to the ramp. We're going to have the force of gravity, which points down, and we have this pushing force, which points to the right. And those are all the forces because we don't have friction in this problem. Okay, now to calculate the work, only the components of the forces that point in the x direction will do work. So the first thing we have to, only the components of the forces that point in the x direction, either positive or negative, will do work on the book. So we can say the normal force, because it points in the y direction, is going to do 0 work on the book. So I'll go ahead and draw the x-axis on this free body diagram so that we can see what those components will look like. So there'll be a force of the pushing force in the x direction, positive x direction, and there'll be a component of the force of gravity that points in the negative x direction. So the work done by the pushing force is going to be equal to the x component of the pushing force times the displacement. And in this case, that's going to be the pushing force times the cosine of theta times d, and that is a positive value because the x component of the pushing force points in the same direction as the motion. Then if we look at the work done by gravity, that's going to be equal to the x component of gravity times the displacement, and that's going to be negative because gravity points down the ramp, opposite to the direction of motion. And if you remember from before, that's going to be, so we have the negative sign there, and then mg is the magnitude of the force of gravity, and then the angle here is going to be the sine of theta, right? And that's something that we can remember from the previous examples with objects on ramps, that the component of gravity that's parallel to the ramp depends on the sine of theta. Right, so then our network is these two added together. So it's the work of the pushing force plus the work of gravity, and really we can say plus the work done by the normal force, but we already know that's 0. And so the pushing force, we've got Fp cosine theta times the displacement, and then the work done by the force of gravity is negative mg times sine of theta times the displacement. Okay, so that's a calculation for the net work based on the definition of work. And the reason why we care to calculate that is that the net work is equal to the change in kinetic energy of an object. Right, and that's 1/2 mv final squared, I'll just call it v, minus 1/2 mv naught squared. But in this case, the initial velocity was 0 because the object starts at rest. Right, so we've got two expressions for the net work. Right, we've got the one that's what the net work is. It's the from the definition of work, and then we've got what the net work does from the work kinetic energy theorem. So we can set those two equal to each other and solve algebraically for the velocity. And when we plug in the given values, we get that the velocity is 0.94 meters per second. Right, so that shows the usefulness of the work kinetic energy theorem.